We introduced the topic of the freezing point depression equation. I'll just stick it over here for reference. So change in the freezing point of our solution is equal to, if we have a Van Hoff correction, then we have a freezing point depression constant. Let's see. Freezing point. And then we have molality. Okay. Let's see. There's not a whole lot of introductory material here, is there? So we'll just take the pre-lab question then and solve it. So here we got a word problem. So we need to extract the information like we normally do. Okay, now we can move on. This pre-lab question. So let's look at what's the question. Calculate the experimental molar mass of the solute. So we're looking for the molar mass of the solute, which is mass per unit mole. So we got to find out of this data these two values. What's the mass of the solute? What's the moles of the solute? And we go back to the top, we have 7.98 grams of lauric acid, which is what? Lauric acid mass is 7.98 grams. Okay. Has a freezing point of 43.75 degrees C. Then when we add 1.03 grams of benzoic acid to that, so this is the solvent. And benzoic acid plus lauric acid. Well, let's see. Not yet. Hold on a second. Benzoic acid mass equals 1.03 grams. Then the freezing point, this is lauric acid. This is lauric acid plus benzoic acid. So this is our solution. And its freezing point is 39.43 degrees C. They must have some fancy thermometers. Get 2 decimal places out of it. What else? Oh, the freezing point depression constant for the solvent. So this one for lauric acid. This value here is 3.90 degrees C kilogram per mole. Now that may look strange to you because we had degrees C per molal. Well, if you put molal in the denominator and bring it into the numerator, it flips. So instead of moles per kilogram, now it's kilograms per mole. Okay. And the reason we want it that way is because we want to be able to cancel units in our calculations. All right. The accepted value for benzoic acid equals 122 grams per mole. That's what we compare our results to. So far, so good? Okay. If we're going to calculate molecular weight, what do we have at this point? We do have the mass of benzoic acid already. 1.03 grams. What we need is the number of moles. Okay. So if we take this formula, delta T equals Km, and we're assuming I is 1, then actually we can't assume I is 1 because benzoic acid doesn't dissociate, not significantly. I mean, benzoic acid has an acid group on it. Some of those hydrogens leave, but not enough to influence the results. So the delta T is what? It's a depression. It's this one minus that one. 43.75 minus 39.43 degrees C. That's delta T, change in temperature. Okay, and our K is 3.90 degrees C kilograms per mole. So we can solve for molality. We can determine the molality of that solution, which should be moles per kilogram. Okay, so what's molality? Well, it's this difference divided by that value. 43.75, 39.43, subtract is 4.32 degrees C per 3.90 degrees C kilograms per mole. So degrees C are going to cancel, and we're left with moles per kilogram, which is molality. Because this is a fraction in the denominator flips when it goes to the numerator. So 4.32, 3.90 divided into that, I get 1.108 molal. Okay, that is the same as moles per kilogram, right? Okay. Well, this is kilogram of solid, correct? This is kilograms of lauric acid. This is moles of benzoic acid. So if we multiply that times the kilograms of lauric acid, we get the moles of benzoic acid. So lauric acid is 7.98 grams. How many kilograms is that? 7.98 grams is 7.98 times 10 to the minus 3 kilograms. Right? Because if the units get bigger, the number has to get smaller by a factor of 1,000. 7.98. So if we multiply this times 7.98 times 10 to the minus 3 kilograms, kilograms cancel and we're left with moles. So let's see, I still got that in my calculator. Yep. 7.98 times. And I get 8.84 times 10 to the minus 3 moles of benzoic acid. So we're back over here. Now we can put in here that value. 8.84 times 10 to the minus 3 moles, grams per mole. So I got 1.03 divided by that number is 117 grams per mole. Okay, close. No cigar. So what's the percent error? That wasn't the question, was it? What's the percent error? Well, it's the calculated minus the accepted divided by the accepted times 100. Percent error. 117 minus 122 divided by 122. 7.22. I get, let's see, minus 4.1%. That's okay. Less than 5% is acceptable. Everybody follow me? Because this is exactly the same calculation you're going to be doing, only you're going to get the data, right? You'll have this value here, it's the same for the K. Then you'll determine the freezing point of the pure solvent, lauric acid. And then you'll add about a gram of benzoic acid and determine the freezing point again. And then plug them in the formula, find out the molality, finish the calculation, and you come up with molar mass. Okay. So how are we going to do the experiment? Well, let's take a pictorial journey through the experiment. It helps to draw pictures. Rather than try to determine the melting point of our solvent in our solution by taking the solid and going to the liquid, we're going to go the other direction. We're going to make it liquid and watch the temperature, record the temperature as it decreases until it freezes. Now, the problem with most organic chemicals, when they freeze, they don't have a really very well-defined freezing point. It's kind of a it's kind of a broad curve. So what you have two options. You're gonna over time, in seconds, we measure the temperature in degrees C. And we start at a higher temperature. I think it starts at 60 degrees. And then every 30 seconds, is it, I believe? So at 0 there's, and 30 seconds, 60, 90, so forth. And the temperature keeps going down until you get to a point where it doesn't change anymore. And we'll take that as our freezing point. You can also observe that, and in these big tubes, get these, they're almost that big, but not quite. You got your material down here, and it's in boiling water. All right. A little less than 100. But once it's liquid, then you take it out and you have your thermometer in there and you keep stirring it because you don't want a differential between cooling on the outside and the inside. And you measure the temperature as it drops. What you're going to see with this tube outside the water is you're going to start seeing some solid formed on the edges right here. That's not an indication of freezing. Well, it is for that locality, but not for the bulk. The bulk has to happen inside here. And you'll see it get cloudy first. Okay. And so you'll have one person mixing it and reading the thermometer, another person recording, and another person maybe timekeeper. So once we get to that point, then if you graph it over time in seconds, you have temperature in degrees C, it'll come down like this, and then it'll kind of gradually go like that. That's for the solvent. For the solution, it'll follow that line, but it'll go down here before it flattens out. So this is the solution. Okay. Now, if there's a discrepancy, if you can't decide where the freezing takes place, the best thing to do is to take a straight edge, draw a line out here like that, draw a line here like this, and that right there will tell you, because if it slopes any on this side, then you'll need to have this intersection over here. That gives you your freezing point. Okay. I don't know if that's in the method. What's that in the method? Yeah, there it is. On page 5. Now, I'm not a stickler about you drawing the graphs. If you want to draw the graph, fine. If you don't, if you want extra points, draw the graph. But you do that for the pure solid, and then you do it again. Once it's solidified, you stick it back in the boiling water, and then you add your benzoic acid, and you mix it with your thermometer. That's okay if you're not too violent. And eventually it'll dissolve. It'll melt and dissolve. Takes a little longer with the solution to get it in liquid form. And then you take it out and do the same thing all over again. Find out what its melting point is. One of the possible sources of error, besides misreading the thermometer and misjudging where the freezing point is, one other major source of error is not getting all of your material down into the bottom. So it's kind of a powder. So if there's any electrostatic charge on the glass, it's going to stick to the walls up here. So that's why we use a special funnel. That's a wide mouth. It's called a powder funnel. And that helps you get stuff at least down past the top of the neck. And then we'll use maybe a liter water bath, so you can get it way down in here deep. So if anything is on the sides here, maybe it'll melt and flow down into the bottom. Try to minimize that error, because the concentration is everything when you're determining the that when you do the pure, it doesn't matter how much gets in the bottom, because there's no change in concentration down here. But when you do the mixture, when you do the solution, if you have any left up here, that's going to influence the concentration, and that will change the temperature. It may not change it enough, hopefully, because you're going to be using crude thermometers, right? So there's a trade-off. Okay, any questions?